Hello again. Welcome back to another session of Rust Munich Remote, the 7th edition now. Today we're going to talk a little bit about embedded drivers. And as always, we have our Discord, so looking forward to see you there. And our guest speaker today is Raphael Bachmann. And yeah, enjoy. I'm going to start in roughly 2 minutes, so that everybody had a chance to pick their favorite beverage, and then we take it from there. All right, Raphael, when you're ready, take it away.
Good evening, everybody. Thank you for the introduction, and thank you for the opportunity to speak here and present you some of the delightful wonders of embedded development. I am Raphael Bachmann. I'm really happy to present here today. Let's jump right in. All right, Rust on bare metal, writing sensor drivers delightfully. First of all, who am I? I am a sort of system software developer right now, having a lot of fun with Rust. And in my spare time, I do a lot of things, but also I chase many projects. Sometimes it happens that I happen to finish a project too. And usually what happens is that I have a new idea and then I just follow that. But eventually I keep coming back to the old projects. Yeah, and this is going to be a recurring topic today. My motto is sort of ideas are cheap. Sometimes implementation is expensive. All right, let's get to some simple roadmap of this presentation today. I will start with a simple context where I come from and present a little bit of hardware development just to have some local environment overview. And then we're going to jump into software development for this kind of target. We're going to look at, have a close look at a sensor driver, which I wrote, and see sort of the benefits and advantages and maybe disadvantages of the embedded Hall project. Then we're going to look at how to test and validate and integrate such a driver. And we're going to finish with some takeaways. For context, here's where I'm coming from. Not geographically, unfortunately, but I started with sailboats, with little remote-controlled RC sailboats out of wood and plastic, and you could steer them over the lake, and then the wind would stop, and you'd have to swim or something. But it always was a lot of fun. And of course, they were human-operated. And later on, I got into electronics and software, so I decided to embark on this project to build a multi-copter firmware, and had a lot of fun with PID control and radio communication. And this project is still up. I wouldn't recommend to use it for anything, but there's some fun stuff in there. And this project also, I worked on it in the academic context a little bit with Framacy, but mostly it was done in C++. And yeah, the drone and the software, it all crashed a lot, but it was a lot of fun. And so with this motivation, with this context, I decided to, just my idea brain decided to come back to both of the things and combine them into a miniature sailboat that just employs some communication, sensing, control, and autonomy so that I can send it on a waypoint mission, and regardless of the wind direction, it would just try to follow the path and eventually arrive at the destination. And of course, for this purpose, I need a lot more sensors than on a multicopter. I need basically all the sensors on a multicopter and then some more. And the benefit is maybe that if it crashes, it's much less dangerous. But overall, it's a more difficult project. So I decided to step up a little bit. And right from the get-go, I also decided this would take a long time and I would probably divert into other projects meanwhile. And this has already happened. So yeah, but I'm confident that I keep working on it eventually. So let's look a little bit, zoom in a little bit on the sailboat. What do we need? Well, we need a gyroscope for wave action and roll and things like that. We need an accelerometer for just more accurate speed measurements and for wave action possibly also. We need GPS, of course. This is required for position and velocity. And we need basically a way to tell where the wind is coming from and how strong it is. And that's the basic set of sensors that I'm sure I will need. Then there is some control magic. I'm not sure yet about it. I'm thinking about it, but not concluded anything. And we have a radio connection to the operator. With full autonomy, this would be sort of optional, but since I don't want to develop a generalized artificial intelligence, I just give the waypoints myself instead of having the boat decide them. And so I need a radio connection, also handy for telemetry. And the both actuators are two servos, basically, so very, very minimal actuators. There's one that controls some rope, which controls some sails, and there's a rudder. That's all. And since that's quite a lot of stuff, especially the orange stuff, which are the sensors, the inputs of the system, I need to focus on one module, settle one module at a time. And I decided to focus on the most unknown first, which is the anemometer. That's the wind sensing device. And just to zoom in a little bit on the sensor even that I'm going to be using, this is a basic differential pressure sensor that basically just senses the differential pressure between the two inputs. And for that, it's not interesting what the physical properties are. The driver has a great data sheet. It's a good company. They even have some Rust crates. So it's a fun thing to develop for. Except they don't have a driver for this sensor yet. The total goal of this will be just to employ 3 of these sensors in an array I'm going to show soon to measure where the wind is coming from. Of course, this needs a brain. And this brain is going to be quite a weak brain, but Cortex M0 processor with 20 hand-solderable pins. It's quite a tiny thing, but has just about sufficient power for this application. And yeah, you can see on the left side some of the specifications: 6 kilobytes of RAM, 32 kilobytes of flash. So it's not a powerful computer, let's just say that. So I got started making some schematics, and it's not too important what these look like. Just this is the core, and then there are some sensors and some helper circuitry. Of course, as always, there need to be lots of stabilizing capacitors. Never forget them. I never understand why I need them, but I just put them. Same thing, but a different view is this. This is a printed circuit board for the sensor. Here you can see that there are 3 big boxes. These are the sensor units, and in the middle there's a brain, and they're all sort of connected over this bus system. It looks a bit funky, everything, but fortunately nowadays it's really cheap and really actually super easy to get going with this. There are open source tools and quite cheap, maybe too cheap, vendors overseas that can print these circuit boards. This is how the whole thing looks in a 3D render. These are 2 different board revisions. The one on the left side is actually the earlier revision where everything was a little more spaced out. And the left board is sort of everything condensed together to have a little less weight on the whole thing, because this eventually will go on the top of the mast of the boat. So it should be light. This is how the whole thing looks physically, unsoldered. The sensor just clips into these holes with a very satisfying click. And eventually, yeah, I have already 3 sensors, and this is the basic layout of the whole thing. I really recommend, if you do this kind of thing, to print your PCBs in black. It's just the really best looking color. If you can afford it, just print it with ENIC instead of HASL finish. There's a red and the golden red and black finish. It looks super good. And yeah, here's some soldering pictures. This is just all for context. On the left side, there's a microscope shot. Not that I would really need a microscope, but we had one at work, so I just tried to zoom in on these things. And this can be useful to detect some solder bridges. On the right side, you can see what happens if I made a mistake in the schematic. I needed to fix the part after the fact. And yeah, of course, that usually requires a board revision, which is why I had 2 boards, especially this mistake. This is a voltage regulator. You don't want to have to fiddle with those every time. Yeah, this is how the finished module looks. A friend of mine printed these little air pods. They are the air intakes, and they are leading the pressured air, the wind, into the receptacle on the sensor. Unfortunately, I only have 3 so far. I need another 3. I have to bug him. But yeah, we are going to just leave the hardware for now a little bit and jump into the software, because that is much more interesting. And also, in some ways, less tedious, because with hardware design, you have to blocking weight on parts and PCBs, and then maybe there's some parts not available. Right now, ST parts, like the processor I showed, are really, really almost not available at all, because there's a global chip shortage. And yeah, so the one thing that one can do during the blocking weights is do software development. But of course, not super easy if there's no hardware. So you can develop the software, you just can't run it. But yeah, still, the software is actually the easy part, so let's jump into that. What is the objective for this software project? Well, I want to make a library that makes it easy to use the STP8XX sensor I showed, and I want to support to configure it, to sample some data, and to do some on-chip data conversion. That is basically the objective of the software we will be looking at. And the first step to do this, as always, is reading the datasheet. Usually, like this is not generally applicable advice, but usually there are, for such sensors, there are operation modes, something like idle and sleeping, as you can see here. Sometimes there's armed and disarmed, things like that. And in my case, the sensor has just an idle state, which is the default state, and it can go to sleep to save some power. It can be triggered measuring one of 2 different modes and will immediately return back to idle, or it can go into a state where it is continuously sampling on a given interval and also with the same 2 options. And when this state can only be exited to go to idle, back to idle. So these are the valid state transitions for the device we have. And maybe just to note the color scheme, because it is in the whole presentation, this same color scheme. The blue lines are transitions, the orange boxes, and also the turquoise boxes are sort of state information. Mainly the orange is the most important part. So what will be the first step? Of course, we do this in Rust because this is the Rust meetup. And what we have to do is, or what I did in this case, was I had some marker states, just marker types, which are 0-sized marker types, just structs with no members. And they are marked orange because they represent each of the states in the state machine. And then I have also these turquoise little types, and they represent the different types of data that can be queried in the different measurement states. So you can see there's one struct here that actually has a member data type, and that member is of type phantom data. It's a ghost type, essentially. And that phantom data has another generic parameter, which can be differential pressure or mass flow. These are the 2 other boxes. Now, the interesting thing to note, which I'll come back to, is a struct has the size of the sum of its members, of the sum of the sizes of its members. So in this case, there are no members, so the size is 0. In this case, there is a member, but phantom data is also size 0. So this struct has size 0. And this has very interesting implications for how to apply this stuff, which is also given by the title of the slide and the next slides, which is type state programming. This is the pattern that we are having at play here. The idle state is a type, but it represents a state. And that seems simple, but it has some really nice implications. We'll see shortly. Just for completeness sake, I added the state transitions here too. In blue, they are just types, marker types for the different state transitions. So to go to the differential pressure sampling state, we take a continuous sampling state and we return an error, these things. But they are not super important. You could also do it without a type alias. You could just do it with a result. Now we come to the meat, to the interesting stuff of type state programming. You can see here a function new that is marked in red, and it takes by ownership 3 arguments. First one is a generic parameter I²C. The second one is just an address. If you know I²C, that's just the address that belongs to this I²C. And then it takes a thing called a delay of type D. And what it gives, it's a self. What is self in this case? Well, for this, we have to look in the first line, and we see that this is an implementation for an SDP8XX with these generic parameters, generic type parameters. And one of the type parameters that is in the output of the new is the idle state. So we see that the state in the last line of code is being set to phantom data idle state, just so there is some storage. But we know that this is of size 0, so it shouldn't matter. And it doesn't matter, but of course, to the compiler, it does matter quite a lot. And if you know Rust, you will know that usually there are ampersands and ampersand mutes everywhere. But in this case, there is not a single ampersand mute anywhere because the arguments to the function new are all owned. And that means that the new data structure that is being produced here has ownership of these resources, and nobody else for now can access these resources. And that means, for example, nobody else can reconfigure our I²C peripheral under us. This sounds like who would do this, but this happens in real life code. Don't ask me how I know. This happens, and then what would that result in? Well, the communication might break, it might not break, it might break in the future. It's essentially, it's a race condition, except worse, because what is being raced on is actual hardware. Okay, let's look at another function. It has the same start as before, so the impl line is the same. So we know that this is also the implementation for the idle state. And I spare you the where clause, by the way, it's a bit long, but you can read it in the code if you really want to. The function here is called go to sleep. And again, it takes a self, but by ownership. Okay, it's mutable, but it takes it by ownership. And it returns a state transition, you can see from the color. And that one will be something that results in a sleeping struct. So the old instance, the old entity will be moved into this function. And the result of the function will be either it worked, then we get the new thing, or it didn't work, then we still have the old thing. So there is no way to call go to sleep in the wrong state. This is essentially what we're doing. The yellow is just actually the business logic. The send command is one command that needs to be sent. And if you know Rust, you'll know the question mark. It will just bubble up the error, not with an exception, just with an algebraic return type. But if it succeeded, then we just return the SDP struct, but the phantom data has changed to sleep state. And also there are no references being used here. So now when we do this in the usage, we have moved in our old instance in type state idle, and we will get a new instance of sleeping, of sleep state, SDP in sleep state. How do we get out of it? Well, the same basic pattern, except this time the first line changed. This is the implementation block for the sleep state. And also where block, yeah, it's long. But the function is called wake up, and it hints exactly what this stuff is doing. And it gives us a sleeping to idle transition. And we can see from the return state return type that what we're returning is a struct with the phantom data set to idle state again. So this is how we get our struct back from sleeping state to idle state. And the yellow part, the commented out yellow part, is the actual implementation. It's too big for one slide, but not much bigger, just a few commands. So what is the general pattern here? Well, operations are available in their state and their state only. So we can call, go to sleep in idle state, and wake up in sleep state. I start to sound like a broken record, but this is really so nice that I just cannot stop repeating it. And the good thing is that the transitions, the state transitions, take ownership. So there are no leftover invalid objects. I'm looking at you, C++ did move. And all of this has no cost in terms of memory, binary, and computation cost. So all of this is enforced by the compiler because everything else would be a type error. But when the compiler is done with the type check, it just removes the phantom data and the zero-sized types. They just disappear. They're not in the binary. And we can even see this when we call the sizeof function. If you know C, you're going to be familiar with sizeof. In Rust, it's a bit different. You have to use the nice turbofish. Well, nice, I don't know, but the turbofish to get at the type that you want to have the size of, and then you call the function, and you get 0 in this case. And that is a hint of why this is actually a free operation. So you get all these benefits at no cost that would be apparent in the product. Of course, there is some developer overhead. And interesting things happen sometimes. This is also a slight disadvantage of this kind of thing. The yellow thing here is completely optional. It's a type signature. So in Rust, you know that type signatures can be inferred. But in this case, yeah, the editor showed me what the type signature was for this NRF24 driver. And yeah, it has a number of GPIOs in there. Then there's, what is there? Like another GPIO, an SPI with different GPIOs. Yeah, but this is the type signature. And it ensures that the things that you pass this TX to know what you're talking about. So it has some benefits. Of course, this is a long ass type signature. I mean, you need a huge screen to show this. Yeah, so let's have an interlude and look at the embedded ecosystem just so that everybody's on the same page. Out there, maybe you saw on Amazon or somewhere on Chinese websites, there are so many sensors for basically anything that can be sensed. And all of them are pretty cheap. And the hardware is usually pretty awesome. I have only very few experiences with hardware not really working. So, and I got a lot of sensors. But usually what's lacking is the software quality. Sometimes there are some Arduino libraries, and then usually they're developed for a while and then they're dropped. So you kind of have to downgrade the Arduino IDE. And overall, it's not a really pleasant experience. And what's worse is if you are developing on a special target, or if you want some more performance out of the thing, maybe asynchronicity, any special requirements really, you're going to have to use the manufacturer provided drivers, but they're not going to play nice with the drivers from whatever manufacturer did the hardware, if they did drivers at all. So you kind of are left with a lot of custom implementations of basically the same stuff all over. I don't know how many SPI drivers I've written in the past. Must be a couple. And they're all the same, except for these little differences. So it's really not an interoperable situation. And it's fun. It's really fun. And it feels like one is doing optimal work because it's like from the data sheet into the code. But of course, productive is not a word to describe it. So the Embedded Hall project, of course, it provides a solution to this, which is still in development, but it's showing a big promise to help with this situation. And what Embedded Hall is essentially a Rust universal interface for basic common peripherals like ADCs and watchdogs and I2C, and maybe also, of course, GPIOs. But it is only a set of interfaces. So these interfaces can be used by drivers, and targets, whatever they may be, can implement Embedded Hall. And that means that the target for which an implementation of Embedded Hall exists can use any driver that has been developed for Embedded Hall. And because of these zero size abstractions, zero cost abstractions that I showed before, this usually comes at no cost, not even low cost. It comes usually at no cost. And this is very important in the embedded ecosystem. But at the same time, it is very flexible. And folks are also still all the time discussing how it can be extended and improved. But yeah, so there's a lot of work being done in this, and we will see some interesting applications of this in the following slides. But first, let's look at an example how this looks. Usually, the yellow stuff are just GPIO pins in this case, and they are moved. So by move, they are moved into the SPI, which means nobody else can touch them. It's like not even look, don't touch. They're completely gone to the rest of the program. And this means the SPI can do with them what it wants. For example, reconfigure them into SPI pins, which is useful. And then when the SPI is done, we pass it along with some other GPIOs into the dark green object, which is an e-paper display. And that's another nice aspect. All these display drivers, they rely on a hall for displays, which is called embedded graphics. And that means that you don't have to deal with different display drivers or different drawing backends or stuff like that. You can just develop the stuff for embedded display, and then it will work with whichever display you choose to use, with whichever interface on whichever target. So it reduces an M times N times O times many things problem to a much less difficult problem that is much achieved through interoperability. So how does this work? Well, it's basically the same patterns from before. We have ownership, we have move semantics, and now it's possible to configure some stuff, but it's impossible to configure it in a wrong way. And because of this ownership thing, each entity sort of owns its dependencies. And what allows this are types, traits, and generics. Of course, as we saw, sometimes they become really huge. One could make the argument that it is required complexity, but of course they are sometimes very huge. And as I said, the goal that we reach by this, first of all, is portability. So I tested my driver first on a really embedded target, as I showed before, but then I just used a Raspberry Pi with Linux embedded hall, which implements embedded hall, and just was able to use print lines and all this stuff. And yeah, it would be at any time very easy to migrate to any target which has an implementation for embedded hall. Some of the embedded hall implementations are incomplete. Some few, like the RISC-V longer nano, as we painfully found out recently. But there's a lot of work being done. And if the board is at all a little bit famous, then there will be at some point an embedded hall implementation. One thing I haven't talked about yet is that the embedded hall does not require, of course, to be implemented on hardware. It might as well be implemented on software. So in this case, you see a unit test from the driver. It's called trigger mass flow read. And yeah, it just makes a command and it makes some data. And then importantly, in the third line of the function, you see that expectations variable where there are just two transactions in there. And one is a write to address 10 of the bytes from the command. And the next one is a read of the data. So we are essentially setting up just a vector. This is a vector. In case you're not familiar with Rust, there's no type here, but Rust can infer that this must be a vector. Because we pass it as the next in the next line to the mock. And the mock is just an I2C fake device, let's say, which just requires the expectations as input, and it will act to anyone who deals with it like an I2C device, like a hardware I2C device or any I2C device. And in the next line, we are already passing mock on to our SDP driver with an address of 10, which is the same address we used in the expectations. And then we ask the driver to trigger some read, which is exactly the read we did in the first line. And we can unwrap here. Usually unwrap is not a good thing, but in this case we are in a unit test. So if this fails, it would just lead to a failing test. And then we call this function SDP release, which just, we're still in idle state because the trigger mass flow sample doesn't change the state. So the release is available in idle state, and it will just release all the resources that have moved into the device. And then we call done. Done is a special thing of the mock. It just asserts that all the actions, all the expectations that we put in have actually been requested. And if that would not be the case, it would also be a failing test. And this way we can sort of model behavior from the driver, from the device, from the real world without having to touch the real world. And that is very beneficial in this kind of development, of course. Another benefit that also has to do with a software emulation of the embedded hall is that we can now create I2C interfaces even without having actual I2C hardware. And this is called bit banging. I have not such a long career, but I've seen quite many bit banging implementations of I2C. Everybody does their own thing. The principle is that one just uses timers, the CPU, and a few GPIOs, so a few digital pins, to just simulate the behavior of an actual hardware device. I would say hardware device is always better if it doesn't have too many bugs. But of course, sometimes, like me in this case, we have a situation where there's simply not enough I2C, or maybe like it was in my case, we had 3 sensors, but they all have the same I2C address. So either you need 3 different I2C peripherals, or you just bit bang the stuff. It's a bit unwieldy working with I2C devices, more than one on the same bus. Or I could have used a multiplexer. Well, I just decided to do it in software, which is completely fine for this application. And as for the code, yeah, it's very simple. Just make a few GPIOs, make a timer, configure the update rate of the timer, and then just construct the I2CBB struct, which is part of the bitbang hall implementation. And because this struct relies on the embedded hall trait GPIO, it also doesn't know that this is a hardware GPIO. It doesn't care. You can pass in whatever you want in there. And you can also pass whatever timer you want. So this is really, really flexible. And in the end, we just do the same thing and create our driver with this I2CBB interface implementation. And the driver doesn't even know that it's bit banging. And it doesn't care because all communication happens over the interfaces. I want to mention one tool, which is tarpaulin. It's a clever name. You can find out how it's named this way. It's just essentially super easy line coverage. Of course, this exists in every ecosystem. It's just a one-liner though, so it's really cheap to use. And right now it's just line coverage, but the guy who makes it is working on branch and MCDC coverage, so this will be fun. And of course, it's always good to aim for good line coverage, but it's also important to remember that it's just a metric. Here you can see an example of line coverage of another driver I did, very simple driver. In this one, I actually had a maximum achievable line coverage. The only line that is red is this line here. This line is not covered by the tests. And of course, it cannot be covered by the tests because it's a phantom data struct with a disabled state type. So it cannot be used in the binary because it is not in the binary. That's just a neat little thing I wanted to show. Another shootout for a crate this time is prop test. Super good crate. It's essentially fuzzing, but using properties that you have to state programmatically to find clever input data for the tests. And then if there is a crash or a misbehavior, the crate prop test will find the minimum input that creates this crash or this misbehavior. So you don't have to do that yourself. And it uses some interesting strategies to find these interesting behaviors. And every time I've used it so far, it's always been very fruitful. Sometimes there are edge cases, but well, an edge case is just also a case, right? So whatever one can get, it's great. So I had this idea, this hasn't happened yet, but I'm sort of thinking about it. One could combine the mocking with a prop test to model a misbehaving hardware device, like a hardware device that just sends random data. And this is essentially what I do in the test I linked above. But it would be nice to have this as a sort of not so manual thing. So to have this somehow automatically generated. I'm still thinking about it. I don't know where this will lead, but this would be maybe a fun project. See, that's what I meant. Actually, I didn't even realize, but it's already the next thing coming up in the back of my mind. It's terrible. Anyway, so what are the benefits? What do we get here from all of this stuff? Well, as I said, I ordered the hardware and did some stuff, but it took a long time. But when I got the hardware, the software was essentially done, and I had employed the techniques I presented, and the software just worked. I mean, this is not supposed to happen. Maybe in other domains this can happen, but that you attach an I2C device and the driver works, that's not something that has happened to me. Maybe it's also just me, but in this case, I was very, very happy that it just worked. And well, as I said, I used the Raspberry Pi for prototyping. That maybe also helped because it's much easier to develop with easy print lines. You can have print lines in bare metal too, but it's a little bit more involved. And as I said also before, I had 3 of these I2C sensors and I connected them to the MCU, which would have been impossible without the bit-banging implementation of I2C. And this also worked first try. And I wasn't even surprised. This is actually the even nicer part. Yeah, you can have a link. There's a link to the project below if you're interested and want to have a look. So to zoom out again a little bit, as we have been doing, why do this? Why fiddle with these types? Why take this on? Well, in my case, some code just bit rots quicker than I can write it. Especially when there's cross tool chains, vendor tooling, maybe make files or build environments. CMake gets out of date, dependencies get out of date. So I just don't even use dependencies. These things happen. And then I want to pick up a project again, but first I have to fix all the stuff I've already done, and it just becomes this messy and difficult thing to get running again. But with this stuff I presented, you can just basically hit cargo build or cargo run, and it just works, or cargo test if you really want to make sure. Yeah. So all of this just increases the confidence in software and the quality and the longevity of it. We have easy unit tests, we have easy mocking, we have easy coverage analysis. We have type state programming, as I presented, super good for increasing the confidence, making it easy to use but hard to misuse. And a large part of this, which I didn't even mention, is dependency management, cargo. So just running a simple embedded project already pulls in so many dependencies that I don't even need to know about. It's actually nice. It's unusual, but it's nice. And the end goal of this is to reduce SAD. And SAD means spooky action at a distance. An example, if you want to send some data to your multicopter, you don't want it to immediately start flying off unless this is the actual command that you gave it. This is spooky action at a distance. I call it SAD. I stole the term from some other field. I don't know. I didn't invent this term, but I think it's perfectly describing what is to be avoided here. And what this will result in is solid building blocks just to rely on for building the rest of the thing. And it means I can pick up a project where I left it. And it means that next time I pick it up, I can build abstractions on the ones I built before. So this means my long-term projects, which I juggle all the time, actually have a chance of success. This was all of it. Thank you. I'm happy to receive some questions in the chat. Yeah, looking forward. Thank you for your attention. I think you may be muted, Bernhard. Okay, stand by. We might be having... there he is.
Let's see if this works.
Yes.
No? Okay. Perfect. Yeah, every update is a surprise sometimes. Thank you very much, Raphael, for giving the awesome presentation. There's one question. How do you use cargo tarpaulin to create PDF coverage reports? If you know.
You
you
append, you just append a -- out HTML, and then you export that to a PDF. I'm sorry, that's not the answer you were looking for. Maybe there's a PDF out option too. I just generate HTML and make it a PDF. But maybe that should be a thing, actually.
There's a small remark. If you use cargo tarpaulin and you have a lot of multi-line statements, your coverage report will be off by quite a bit. So if you use cargo tarpaulin, try to only use single line statements, so no additional line breaks, or opt in for the nightly coverage report that's built into Rust, which is way more accurate. I can share a investigation write-up I did quite a bit ago. So if you're interested in that.
Yeah, at least I am really interested in that, because as I noticed, sometimes the reported coverage is a bit off of what I would expect.
Yeah, it's quite substantial. Like you can easily go from 95 to 60, 65% if you have a large code base with complex function signatures.
There's some stuff coming up with... oh, sorry, I didn't want to...
No worries. Beyond unit testing, did you try out benching? If yes, which framework did you use?
An interesting question. What would I even bench? I mean, the hardware performance, I mean, what would I even bench in this case? I have a driver, and of course I could mock the hardware and just try to see how much overhead comes from my driver. Yeah, that would be interesting to do. Thank you for the idea. I guess Criterion might be good for this, but I'm actually, this is not something I'm familiar with too much. Bernhard, maybe you have experience with this.
Yeah, to some extent. In embedded, there are two things that you should keep in mind. You have your hardware-dependent, kind of I/O API, which is just like the I/O API is just way bigger than you used to on a desktop. So what you usually do is you try to isolate your states from your I/O, and that way you can kind of, to some extent, fuzz your state machine, but with arbitrary I/Os. And for the I/Os, you either have a hardware bench where you test functionality, or you have hardware in the loop where you simulate the peripherals, but that's a bit like beyond the scope of a pet project. So that's something you would do with your full-time embedded engineer or embedded test engineer.
In my case, I would need something that generates wind.
Yeah, but you would remove the wind and like the differential pressure sensor and just emulate what that sensor would respond on your SPI.
Yeah, of course. I mean, it depends on the level of fuzz of the abstraction I want to go to. Yeah.
So it really depends how much effort you want to invest. For a pet project, I would probably not bother to and just try to writing that kind of integration to emulate or simulate your sensor devices with coherent data, especially when you have many sensors. It's a lot of time. You probably not waste, but you spend more time developing your test environment compared to your actual code. And at some point you have to say, yeah, life is short. You need to, it's a pet project. It's supposed to be fun. And at that point you have to say, well, maybe focus on the functionality over 110% unit test coverage, 110%.
Yeah. I totally agree. But there are some really nice projects out there for doing this with drones, where the firmware runs on the computer and the drone is in a physics simulation, like Gazebo or AirSim by Microsoft. Super fun projects. I've looked a little bit into it. It's like, I don't know if I would just fly around with the drone if I managed to get this running, but I think it would be super useful to develop something like this.
Yeah. I have a little bit of a strong opinion about drones. Like, I find them for pet projects to be too complex to really be able to comprehensively cover the topic. And yeah, to me, they're just not that interesting that I would go for a full-time job in that area.
Yeah, there's definitely a lot. Like with the sensor fusion, you can have just a job doing sensor fusion, and it's just one aspect. Or pit control, you can have just a job doing pit control. And to be honest, my drone project, it kind of flew like a pet project. So
What do you mean by that?
oh well, just
like a rock, or
no, it flew. Not like a rock, but sometimes like a rocket, and then it would stop. I mean, there was problems with the sensor fusion. It was drifting, so sometimes you'd need to manually compensate. So it helps being good with the controls, but then sometimes things happen, and as I said, there were some crashes. Yeah, it's hard to do this as a pet project, but it's becoming progressively easier. The sensors, the BNO 080, I think, by Bosch. It's a great little sensor. I've just tried it out. Integrated sensor fusion, so you don't have to do a thing. And you can just, with 100 hertz, get your data. It's a bit slow. 100 hertz is not terribly fast, but it's well fused, so you might get around working with that. And then there's super cheap GPS devices if you want to go in that direction. There's pit control libraries. There is very cheap actual hardware, very cheap drones. So it's becoming more and more feasible to do this. Radio connection is also a topic. There's some really amazing hardware out there just to have some radio connection for do-it-yourself projects. So yeah, you can make a crappy drone with pretty low effort.
Yeah, the part that would interest me the most is getting back into the sensor fusion part, like Kalman filters and particle filters. And it seems there's still a bit of a void in the Rust ecosystem in that area. So yeah, that might be something to dig into at some point.
Not me, please. I mean, there's a Mahoney filter or Magic filter. I think Magic filter by the awesome Japarik. He has done a filter implementation of that. And I think that what was it? Which project was it? Micromath, the Micromath project, which supplies some floating point math and vector math primitives for no standard targets. It was forked off or split off the accelerometer crate, which is a generic interface for accelerometers. So there's also being done some work to unify these sensor interfaces. And yeah, these crates have continuously updates, some of them. And yeah, this is more a topic I think is a bit lacking right now, math on no standard targets. But it's a really hard problem. Like I looked into it briefly and I saw some GitHub discussions regarding libm and floating point unit, yes or no, and just seems to be very, very hard. But even that, I mean, it's already quite good. Can always improve.
Yeah, there's always room to improve. It's really surprising the difficulty of floating point implementations and using the correct rounding modes and general correctness. That's often, like, from an end user perspective, like as a programmer, your UI is essentially the programming language, and there you only have a F64, F32, maybe a F16 that might pop up in the future. But the underlying parts are really, really non-trivial. Like how to assure that multiplications have the same results across targets, so that you have the same, if 1 times 2 is 2 on all targets and not 1.999999, for example. Yeah. Anyways, thank you very much for your talk. I think we ran out of questions quite a bit ago, so I'd be happy to continue this in the Discord channel, and yeah, hope to see you around.
For sure. Thank you a lot. And thanks for making this a platform to speak on. And see you around.
Awesome.